Alrighty, guys, can you hear me? Are we ready for the second half? Try to catch up a little bit here. So what we're going to be doing now is we look at this example and then we look at this game. We're going to try to look at this example, try to place these tools and techniques that are the math objects that are needed to understand these examples from a theoretical point of view. So this is what we're going to be doing now. We did the example, we did the numeric, we did numbers. Now I'm going to try to introduce new concepts and then try to use these new concepts to ultimately come back to American derivative pricing. But there are lots of new things that are coming in to study that are needed to come in and describe and study these problems. So there'll be some new concepts coming now, and I'm going to try to go over it, try to talk about some of the pitfalls that I've seen students struggle with in the past. But so a tool from martingale theory is what's called stopping times. Like so in derivative pricing, these are the model. In derivative pricing, these stopping times, the model the exercise time, and in the game with the die, the model these modeled when to quit. Right, you call it stopping times in general. The mathematical object that we are studying is called a stopping time, right? So this is a random variable. And this is important, it's a random variable. But it's a little bit different, perhaps. But so it's a random variable, right? So, and it's denoted by tau. If you have not seen that before, the tech code is tau. It's a random variable. Tau goes from omega. That's our sample space. And it takes values between 0, 1, 2. And then the little bit tricky thing here is that it also takes the value potentially, which is plus infinity. Right, so these ones here, these are the natural numbers. And then you have infinity. This random variable, tau, is called the stopping time. If when I look at the set where tau is equal to n, right? So remember this here is just shorthand notation. This is just This is shorthand notation for a much longer expression, which is those omegas in omega, such that when I plug them into tau, I get n. This set here belongs to Fn for n in the natural numbers. That's the definition of a stopping time. And by far, the most important example is the following. This is called first passage times. By far the most important class of stopping times for say for k a constant and say maybe we just take the stock price or stochastic process in general. So this could be an adapted stochastic process. This could be the stock. Could be the stock that we work with. We're going to define tau of omega. We're going to define tau to be the first time, the first n, such that the stock price, say, is bigger than k. And we define tau of omega, right? So this is tau of omega, this is tau of omega, and we define tau of omega to be plus infinity if, well, if the stock price never gets above k, if Sn of omega is less than k for all n in the natural numbers. Like this last part here, the last part means when we're looking at the infimum over the empty set, this is defined to be plus infinity. So this is an example of a stopping time. And if we return back to, say, the binomial model that we had before. So in a binomial model like the one we had, you have the tree. Say this would be the tree. Then I could pick a k. So here, if this was, what do we have? We had 4, 2, 8, 16, 4, and 1. We could put a k in. We could put a k in like here. So if I took k to be, say, what was it, 5? Was that the exercise we had? So 5, for example. Then what would I get? In this particular, I have up. So here my omega, this is heads, tails, heads, tails, right? I have my two concepts. So what is my tau of these 4 elements? Tau of heads is equal to what? Yeah, I'm looking at head. So I'm looking at the path that goes from 4 to 8 and 8 to 16. Along that path, when is the first time that the stock price got to be over or equal to 5? This is time 0, time 1, time 2. Yes. Awesome. So this is all equal to 1. Okay, so now let's do the other one. Tau HT. So now we're going to go up and down. When was the first time that path came above 5? Also 1. Tau of, what is left? Tails, heads. When was the first time that this path came above 5? It never did. Okay, so then what is tau of TH? It's the empty set. Yes, so it's equal to, what is tau equal to? No, it's not 0. It's not 0. What happens when you have the empty set? You get plus infinity, right? Yes, very good. And what happens if I do tau of tails? Well, we never get above, so we are stuck at plus infinity, right? So this is my stopping time. So maybe we should just make sure that it really is a stopping time. Like so let's just check that tau indeed is a stopping time, right? Well, we need to we ought to check. We ought to check that we have stuff like this. So maybe we should. So maybe I do it in 2 steps. So let me do it in step 1. If I check that tau n less than n belongs to Fn, then I'll also have that tau n. So this is for all n. Then I'll also have that this set belongs to Fn. This condition that you see here, this is the one that one uses in discrete time. So given that you're going to be in continuous time in the spring, and we just make sure we also know what that condition is. So in continuous time, you won't see this condition, right? Because in continuous time, typically these sets here, the null sets, not in discrete time, but in continuous time. So instead, what people use is you will have tau less than or equal to t belongs to ft for any t. So you see that you replace the equality sign with a less than or equal to. So let me just show you that indeed in discrete time, this is tomato. It's the same thing. It doesn't matter whether you write one thing or the other thing. So this is what I'm saying here. If I can test that tau less than or equal to n is an Fn for all n, then also get this part. And the way to do that is by saying, well, tau n less than n belongs to Fn, and tau n tau less than n plus 1. This is then going to belong to Fn plus 1. I have this property, I'll have these two. And then I can use that fn plus 1. So tau n less than n belongs to fn, and this is inside fn plus 1. So I'll have that both that set and this set belongs into fn plus 1. So then what can I do? I can look at the complement. If I have a set in there, the complement is in there. So tau bigger than n is going to be an element inside fn plus 1. And then if I look at tau bigger than n intersection with when tau is less than or equal to n plus 1. So here it's less than n equal to 1. Here it's bigger than, strictly bigger than n. This must be the same as when tau is equal to n plus 1. And this apparently is a set inside fn plus 1. So if you have properties like this one, you can get that the equal already inherits it. And of course, if I have the equal one, I can start taking unions and I'll get the less than or equal to part. So I'm going to test out this property here. So step 2, let's check that tau n less than n does indeed belong into fn for any n for the first passage time. Well, again, I can look at the complement. So if I look at when tau is bigger than n, so this means that has not tau is bigger than n. This means we has not, so S has not reached K by time n. Right. Tau is the first time S reaches the level. Apparently on this set, it hasn't happened. Right. So if I'm looking at S m, well, it has to be less than K then, and it has to be like that for all prior times. Like in these elements here, this is something that belongs to fm, and fm, m runs from 0 to 1, so this is something that's inside fn. So that's the proof. So first passage times are stopping times. Sometimes it can be instructive maybe to think about we could try to think about like, so what's not a stopping time? Any ideas on what could fail to be a stopping time? So what's not a stopping time? So here what we're doing is we're sitting and we're keeping track of, as we go along, we're asking, like, so we're moving to the right, say. In this example, start out here. Can we identify if the first time that the stopping time, the first time that the process has reached level 5 has happened, and we look, okay, the only thing we have is 4. Can we identify whether or not the stock price has reached the level 5? And the answer is yeah, this hasn't happened. And then we move along, come up to here. Can we identify whether or not the stock price has reached the level 5 for the first time. And yeah, I mean, when did that happen? It depends on the first coin flip. At time 1, if the first coin flip was heads, it happens at time 1. If the first coin flip was tails, it hasn't happened yet. And so on. So there was a suggestion in the chat. If the K is too high, no. We proved here, like the proof that we just gave. The proof that we just gave works for all K. We're not making any assumptions in this proof here that K has a certain size. Right? This works for all K. The question is, can we come up with something else that doesn't have this property, that as we move along, we won't be able to identify whether or not the event has happened. Well, here we're looking at the first time that you get along above the threshold 5. Instead of looking at the first time, we could try to look at the same thing would the same thing would work if I changed K. If I change K to say 8, if K is equal to 8, then as we move along, we get up to time 1. If K is equal to 8, we are at time 1. We would still be able to answer the question whether or not the stock price has gotten at or above 8 at time 1. Could I change the word first? Right? That is what is highlighted here. First. Instead of first, what could we try to put in? Well, kind of what is the opposite of first? It's last. So if I would put in the last time, would we be able to answer the questions then? So we're sitting here at time 0. Will I be able to say that the last time that the stock price got above 5 has happened? If I move out to time 1, would I be able to say that, well, the last time that the stock price got above 5 has either happened or has not happened? And so this is not possible because at time n, we don't know what's going to happen in the future. So we can't answer the question about the last, we can't say that at time n whether or not the stock price has gotten above 5 for the last time. We can say whether or not the stock price has gotten over 5 for the first time, but not for the last time. So last passage times. These guys are not stopping times. They're random times, but they're not stopping times in general. Okay, maybe we shouldn't. Sometimes it can just be useful, maybe, to think about. Like, being a stopping time is something that's quite special. Lots of random times, like lots of these random variables here, they will not be stopping time. This property here is really special. So what are these stopping times good for? Let's try to do some work with them. So you should not. Well, I had a warning sheet somewhere. So this is just this is one of the pitfalls I've seen students fall into. So this is a warning. While similar in some ways to constants. Don't treat stopping times as constants. Let me just give you an example. Let me just give you an example for some of the problems that could lie ahead. If we do a symmetric random walk on the integers. Right, so I take my size, here IID, and it's symmetric, so the probability to half of being +1, and it's a half of being -1. Now I want to create my my symmetric random walk on the integers. I'm going to say I start up at 0, and then I'm going to define recursively what my m is. It's going to be the previous one plus my psi. So it starts out at 0, and then it can go up or down, +1, -1, go up and go down, +2, 0, -2, and so on. This is my symmetric random walk on the integers. I'm going to look at tau is going to be the first time that my m, this is the first time that m becomes, say, 1. Let me put in that level. So keep in mind, this is a warning. This here is my threshold from before. This is equal to 1. So I have a symmetric random walk on the integers, just a bunch of coin flips. Every time I flip heads, I go up by 1. Every time I flip tails, I go down by 1. I'm looking at the first time that this stochastic process gets to be 1, or yeah, it gets to be 1, right? It starts out at 0, so it's the first time it gets to be 1. So let's try to come up with some maybe conjectures. This is a random variable, so I want to know what's the probability that tau is finite. Do we get to this level? Probability 1, or what do you guys think? What do you guys think? Are we going to get, is this symmetric random walk ultimately going to make its way to 1? So we have a random variable, like this tall here. He goes from omega till 1, 1, 2, and then plus infinity in here. My question is, the value plus infinity, this is when you don't, he never reaches the level, the red level. Do we think that such a structure here is ultimately with probability 1? I mean, there are lots of elements in that would never reach the level 1, right? If I look at tau of heads, that element, if I just see heads, it's never going to make it to 1. But this is equal to plus infinity. Likewise, if I see the element heads, no, not heads, tails. Sorry. So if I see tails, heads, so then I'm here, and then I see tails. This is also equal to plus infinity. There are lots of elements. There are lots of elements in the sample space that never produces M to be at the level, the red level. Any guesses on what the probability of getting up there is? That's what I mean by conjectures. Any guesses? A half? Oh, Han, be careful. There's no N. There's no N here. There's no N in here. What about if I were to compute the expectation? How long time would we expect? How long time would we expect that it takes for the process to get up to level 1? So the correct one here is, this is actually 1. And the correct one here is plus infinity. So there is some, so this is something we need to prove, right? So this is, these guesses and conjectures, they need proofs. But again, we're back into this warning here, right? Don't treat these stopping times as constants. And here's an example. So we have that mn takes, so where does mn takes values in, well, it's mn can at most be n, and it's also above minus n, right? So it goes from minus n to minus n plus 1, up to 0 to 1, all the way up to n. Whereas, given that tau is finite, if I put in m tau, given that tau is finite, what is this equal to? What is m at the time when it crosses 1 for the first time? So this would be 1, yeah. So this is not random. So you have that Mn is random because it takes these values here at various probabilities, but M tau is constantly equal to 1. And there's no randomness in a 1, right? So what happens is that you mix. So what happens is that Mn is random, tau is random. You mix them, and you get M tau is not random. So this was one warning. This is not random. Mn is. So this was like that was warning 1, and here's the second warning. We have that we've seen that in various forms and shapes. We have that Mn is a martingale. Mn is a martingale because if I calculate the conditional expectation given the coin flips up to time n, I will use plug in the definition. So here I'll get Mn plus psi n plus 1 given Fn. And then I'll use linearity. Right, and then I'll use that Mn is measurable with respect to Fn. So then the conditional expectation just becomes Mn. And for the second term, I'll use that psi n plus 1 is independent of Fn. So the conditional expectation just becomes the unconditional one. And then I'll use that it's a symmetric random walk. So the probabilities of being 1 and being minus 1, those are both a half. So the expectation is equal to 0. So this is a martingale. And in particular, M0 is the same thing as the expectation of Mn. But this is the same, saying that 0 is equal to Mn expectation. But you should contrast this with, if I look at the expectation of M tau, what is that equal to? Well, M tau is equal to 1. So this here is equal to 1. So while Mn has expectation 0, M tau has expectation 1. So these are two things that I have seen students having, some students have had issues with in the past. And this is my way of trying to warn you guys a little bit that these stopping times, they are not to be treated as constants. If you do that, you're going to run into potential problems. We did it in this example with the symmetric random walk. This example with the symmetric random walk, again, going back to our textbook, the symmetric random walk, this is a large part of section 5 in our textbook. This is a large part of this chapter here. So this is something that we're going to be spending quite some time talking about. It's probably going to be next time. So So this here, this needs proof. I asked you this to try to help you build up some intuition, like what, and how would this, for example, change if I started putting in a skewed symmetric random walk? So instead of probabilities 50-50, I'll put in like a probability of like, I don't know, 80% for going up and 20% of going down. Then there's a tendency on these paths to move up relative to the tendency to move down. Okay, so if there's a tendency to move up, it's going to become more likely that you see the level 1. One could also have changed this, so instead of k equal to 1 here, we could have moved it up, and we could have had like k equal to 100. But you see, the stuff I wrote in red, which is correct, there is no mentioning at all about k here. So there's no mentioning of k here. It doesn't matter apparently when p is equal to half, whether I have 1 or I have 100. You're still going to reach it, and the time that that you expect it to take to reach it is going to be infinitely long. Any questions or comments on this part? Yeah, okay, so let me try to elaborate a little bit on this. I have seen students in the past also struggling with this. So note, if I have P of tau finite, does that imply that the expectation of tau is finite? Is it true that if the expectation of tau is finite, does that imply that P of tau is finite? So here I have a random variable, which is finite with probability 1. Does that imply that the expectation is finite? If I have a stopping time that has or a random variable that has a finite expectation, does that imply that the random variable is finite with probability 1? Well, this one here is this one here was in our example. Example says no. Right, because in the example, I have finiteness, and that implies nothing about the expectation being finite. What about the second one? Well, keep in mind, what is the expectation here? The expectation. So what if? So this is the example says no. Okay, so this is not true. And what about this one? Well, if so, say that the probability tau being finite would be less than 1. So we're working on the second one. Say that the probability would be less than 1. Okay, that means that the probability that tau is equal to plus infinity, this is positive. But if the probability of tau being plus infinity is positive, what does that say about the expectation of tau? Okay, so there's a little probability that tau is equal to plus infinity. Okay, so what is the expectation?
Infinity.
Yeah, right. So this here is correct. This is correct. This one here, this is false. It amounts to this is similar to an early homework. You can have a function, say from 0 to 1 into this can be finite. You can have a finite function, but when I integrate from 0 to 1, this can become plus infinity. So you can easily have a function that's finite, but then when you integrate it, it blows up to plus infinity. And the same thing is true here. You can have a function, you can have a random variable, which is finite, but when you integrate it, it blows up. So then, is this an outlier case? I don't know. This is these identities are quite famous. If you want to Google something like that, try to Google the Wald identities. That's the name in stochastic analysis that is assigned to what these properties or to what these ones here. We're going to do this. They're going to come. They will come later next time. Okay, so I try to give you guys heads up. Like in the next portion of the class, we're going to be using we're going to be developing and using results related to stopping times, and please don't treat them as constants. If you do, you're bound to make mistakes. So don't do that. Okay, so are there questions before we push on with? So the next thing that's going to come is tying the martingale property in with stopping times. So the goal is to get to something called Dupes optional sampling theorem. Right? So this is the next big theorem is called like for the Radon-Nikodym derivatives. These theorems you come with names. They call Dupes, and it's called optional sampling theorem. Optional. And the word optional, there's something that this theorem this works for what's called optional times. They work for optional times, and these include stopping times. So the reason it is called Dupes optional sampling theorem is because it's written for a class of random variables that are called optional times. We're not going to have a need for them. But a special case of optional times consists of the stopping times that we've just discussed. So the how to put it? Where should we start? How do we get? Well, one thing we can do is so recall that a martingale. We call that M. This is a martingale if E of M n plus 1 given Fn is Mn plus regularity conditions. And then so from here, so we've seen that this implies that the expectation of Mn, say plus 1 is equal to M0. Like martingales have a constant expectation over time. So we've seen that, but so now let's try to turn it around. So what if say N satisfies the expectation of Nn is N0 for all N. What if this is true? What if this process satisfies this? Is this stochastic process martingale? Like we have been using the top part, this is our definition of what it means to be a martingale, plus regularity conditions. So I'm pushing the regularity conditions aside. Right? So we've seen that this implies that martingales have this constant expectation property over time. There's no conditioning in this part. Okay, so now I'm turning it around and I'm saying, what about if I have a process with constant expectation over time? Does that imply that I have a martingale? Han, what do you think? You wrote it's not a conditional expectation. That's true. It's just a regular expectation. And what about Wang? Wang says no. So I'm on Wang's side. So the answer is no. So then we should back this up. So let's give an example. This is an example, I think, from one of your last homeworks. If I take, there are many examples of this. But if I let them be IID normals, then we know that Mn, so M0 is 0, Mn plus 1 is the previous one plus the Brownian motion plus the delta Bn. This is a martingale. What about, okay, so that is a martingale. So let's try to define N up here. If I say N is just my N times Mn. Then what? Then, well, the first thing we observe is if I compute the expectation, this will be the expectation of N Mn. And this is a constant, each travels outside, and I'll get the expectation of Mn. Right, but Mn was given to be a martingale. Mn was given to be a martingale, so we have the implication, given a martingale, I know that it has the expectation property. That is just the expectation at later times is just equal to the initial point, and the initial point was 0. Right, so this is equal to 0. So okay, so we have a stochastic process, and it has this property that it has constant expectation over time. What about the martingale property? Is N also a martingale. Well, let's try it out. If I compute the conditional expectation, given given if n, so take it one step later, given if n, and see what I get. Here I'll plug in definition again. So now I am at n plus 1 given if n. So again, we have a constant. Constant goes outside. And I messed up. There should be an m here. I have plugged in the definition of n in terms of m and this constant. And now we use this as a martingale. So this will be n plus 1 times mn. And if I wanted this to be a martingale, what should I have gotten here on the right-hand side? Well, I should have gotten n, but I don't. There's like an extra term. There's this n plus 1. For this to have worked out, this plus 1 here should not have been there. So the answer is no. It's not true. So if I have a stochastic process that has constant expectation over time, this is not going to give you the martingale property. The martingale property is much stronger. You know that all martingales have constant expectation, but not all processes with constant expectation are martingales. Questions on this example here? So what we're going to see now is another example of how constants are different than stopping times. So let's do another calculation that is related. So this is a little, I don't know, call it a lemma. Maybe we should call it a lemma. If I take a martingale, maybe I should call it m. We're going to take a finite horizon martingale. So I'm going to take a martingale. N is just some natural number. Let this be a martingale. I'm going to say tau goes from omega, and I'm going to say that it does not take the value plus infinity. It takes the values 1 to up to n and be a stopping time. Then, if I am to look at the expectation of x at that random time, it's going to be x, it should be m at that random time, it's just going to be m0. So I have a martingale. If I evaluate the martingale at this stopping time, I'm just going to get the same property as if I evaluated it at a constant time. Okay, and the proof, the technique that goes, that's why I wanted to show it to you, that the way that the proof goes is very, very typical for this sort of calculation. You're going to split you're going to split omega, you can write this here as, because tau takes on these different values, you can write this here as where tau is equal to 0 union, tau is equal to 1 union, and then tau is equal to n. So that's the key. And so when you compute, if you were to compute the expectation of x tau, keep running x here, it should be m tau. How would I do that? Well, I would split according to this. So I'll write an indicator for where tau is equal to n. This would be my disjoint splitting, and so I would sum then from n equals 0 to capital N, take an expectation. And then I'll have on the set when tau is equal to n, I would have mn. On the set when tau is equal to n, m tau is going to be mn. Okay, so then I can use that m as a martingale. So here I'll use that the conditional expectation of mn given fn, this is my m little n. I can plug that in here. I can plug that in here. So I'll get m n given f little n. And then we can move on. We can use that this is a stopping time. So we have that the set tau being n, this is exactly an fn measurable set. So this guy can go inside, the sum can go outside. I'll have then the expectation of the conditional expectation of tau being n, mn given fn. And then I can pull the sum inside. I get a disjoint splitting of omega according to the top part. This would be the expectation of the conditional expectation of mn. Right, the sum here, I pull it outside, I can put it back in here. Then I'll sum up, this is m capital N, I'm summing over little n's. I'll just get the disjoint splitting of omega. And all in all, the expectation of the conditional expectation, this is the unconditional one, this is E of mn, this was a martingale, this is m0. Questions on this lemma? So again, one should watch out here because look out for the assumptions. This here does not work. If you go back, so just look out for the assumptions. Look out for the assumptions. Look out for the assumptions if I would have in our example, so consider from the symmetric walk on the integers with tau being the first time that what do we call the process? So it's this example we had here. So we had the symmetric random walk on the integers. Watch out, because if this was the first time that this would be 1, we would have that the expectation of m tau would be 1, which is not the same as m0. And the lemma says that if I have a stopping time like this one, I have the property that m tau is exactly equal to m0 if I have a martingale. But here is an example that shows, in that previous example, that m tau, this is constant equal to 1, and that's not m0. And that's because this stopping time that you have up here, it does not satisfy that it takes values between 0 and up to some capital M. Right, so that's what I mean, look out for the assumptions, right? So to use this lemma here, you need to have the property that the stopping times do not take values that are arbitrarily large. There has to be some upper level where you get a cutoff. And the counter example was the one we just talked about. So the key result, which is what, so this is the next lemma, but now we're out of time. The next lemma is that if mn if mn is adapted and integrable, well then if the expectation of m tau being m0 for any tau stopping time tau of omega belongs to some set 0, 1, 2 up to n. This implies that m is a martingale. In other words, while it is insufficient to have a stochastic process that has constant expectation at constant times to get the martingale property, that is insufficient. It is sufficient, however, if instead of these deterministic times n, you can plug in stopping times. If you have this property here, you're going to get the martingale property. So again, there's a distinction between stopping times and deterministic times. I think this is a good place to call it quits for today. Are there any questions in the last few minutes? Are there any questions or comments in the last few minutes? So next time we will redo some of this stuff one more time, and then I have to prove these properties that we had about the first passage time on this symmetric random walk. So we'll do that, and then ultimately, after we've done that, we will circle back and we'll reapply the stopping time theory and this Stoops optional sampling theorem that we're going to get to in a minute. We will reapply that to pricing American options. Are there any questions before we? I should say that we have office hours on Thursday morning at 10:30. So you're more than welcome to log in there. Are there any other questions or comments? Okay, then hope to see you guys on Thursday. Have a good day.